Good morning, dear students. My name is Ferhan Mazher, and today is the 1st December 2020. And right now, I am with the 10 Cambridge class, and the subject we are studying is Physics 5054. We are studying the chapter of sound, and yesterday we have done some work on this chapter, and we have done two experiments, the bell jar experiment and another experiment. And today we want to study a little bit about the theory about the sound waves. And the first thing which we want to know, which we want to learn and discuss with each other, is the reflection and the echoes. Now, we talked a little bit about the echoes yesterday, and today we are going into it again. So, you see, the sound waves, when they travel, uh, so they travel in a medium. For example, the sound waves can travel in air, the sound waves can travel in liquid, the sound waves can also travel in solid. So, when the sound waves are traveling in air and, for example, or in water, and they come across another body whose density is different, or mostly if the density is more. So what happens from the surface of that body, the sound waves will be bounced back. They will be reflected. And when they are reflected, then you can hear that sound again. Whatever the sound was. Uh, so there is an original sound, and then from a rigid body, the sound waves which are reflected, if you hear them again, these reflected sound waves, uh, they are called the echoes. Okay, so for example, here are some technical things which are showing on your screen. You can read them also. That the sound waves are reflected well from hard, flat surfaces such as walls or cliffs and obey the same laws of reflection as light. We discussed it yesterday. We did the experiment of the reflection of the sound wave. The reflected sound forms an echo. If the reflecting surface is nearer than 15 meters from the source of the sound, the echo the echo joins up with the original sound, which then seems to be prolonged. This is called reverberation. Some some is desirable in a concert hall to stop it sounding dead, but too much causes confusion. Modern concert halls are designed for the optimal amount of reverberation. Seats and some wall surfaces are covered with sound absorbing material. You must have seen whenever you go in a theater or in a cineplex or cinema, you find that the walls, they are not just straight flat walls. They are always covered with some material. So so it reduces the reflection. Okay, so wherever they need reflection, they leave the surface, and uh, where they do not want the echoes, they cover it with some material. Okay, so the basic idea, you should understand that whenever the sound is traveling, the if some rigid object comes in their path. For example, let me show you. Let me open a new one. So whenever, for example, if this is the sound wave, and if the sound wave is going in this way, wait a minute. Okay, for example, if you have a source of sound, and here we have a rigid body. For example, let me show here. For example, this is a wall. Okay, and for example, uh, suppose From here, a sound wave is coming. So this is the sound wave which is coming, and this is the sound wave basically. So this sound wave will strike this surface, and from this surface, uh, it will go back. Okay. So from here, it will go back. Okay. So this orange color line represents the sound waves which are coming. And from this rigid body, they will be reflected, they will be bounced back, and they will go back. This green color light shows that the sound waves are going back. So if a person is standing here, for example, a person is standing here, let's say here is a person who is standing here. So he produced that sound, that orange color wave, and that's he will hear obviously when he will speak something, he will hear it, and from this rigid body, the sound waves will be reflected. This green color thing is showing that, and he will hear the thing again. And when this will happen, when you hear the reflected sound waves, they are called echoes. If the distance between this person and the wall is less than 15 meter, if the distance between the man who produced or the source of the sound and the wall is less than 15 meter, then what happens that the the sound, the echo reaches back very quickly, and the original sound is still there and the echo is back. So you will get the feeling that whatever you are saying, that is being prolonged. You might have experienced whenever we go in a music concert, they open the echo. So when they open the echo, the sound becomes prolonged. So the thing repeats itself again and again, and they are mixed together. The original is still there, and the echo is also there. So that is called reverberation. So I hope you have understood. I hope that you have understood it.
Can you please repeat
Do you
the
understand this
reverberation?
reflection thing?
Yes, sir.
Hello.
I've understood the reflection thing, but I am not clear with the reverberation.
So your sound is too faint. Okay. So then another important thing is that the sound, the speed of the sound, the speed of the sound in different materials can be different. The speed of the sound, for example, if we are talking about air, the speed of the sound will be, as you can see in the table, 330 meter. And in water, it's like 1400 meter per second. And in concrete, it is 5000 meter per second. And in steel, it is 6000 meter per second. So you see, clearly from here, we can conclude one thing, that the speed of the sound in the gases is slow, and in the liquid it is faster, and the when you go when the sound is traveling in the solids, it is very fast. Okay. So the speed of this is the behavior of the sound waves. So don't forget this behavior. It is tested in exams also, that the sound travels in the, for example, in the air, it travels with the 330 meter per second. Sometimes they say 300 meter per second. Three, around about 310, 320, 330 meter per second. That's the speed of the sound in the gas, in the air. And it will be faster in the liquid. As you can see, water 1400, in water it is 1400 meter per second, and in the solid it's like 5000, 6000. So this behavior of the sound, you should remember this. Okay, so never forget this, because this idea that the sound will be traveling the slowest in the gases and the faster in the liquid and the fastest in the solids. This idea is being tested in the exams also. Okay, the speed of the sound depends upon the material through which it is passing. It is greater in solids than in liquids or gases because the molecules in a solid are closer together than in a liquid or a gas. Some values are given in table 13.1. We have already discussed that table. Okay, so for example, another very important thing about the speed of the sound is that we can find out. Let me show you. So in the air, the speed increases with the temperature. Remember this thing, okay? In air, the speed increases with the temperature, and at high altitudes, where the temperature is lower, it is less than at the sea level. Changes of atmospheric pressure do not affect it. So see, very important information. Very, very, very important. In air, the speed increases with the temperature, and at high altitudes where the temperature is lower, it is less than at the sea level. That can be an MCQ. Changes of atmospheric pressure do not affect it. An estimate of the speed of sound can be made directly if you stand about 100 meters from a high cliff. So this experiment, here he wants to show us, this can be a question in the ATP also, that how to estimate the speed of the sound, and it's very easy. You see, if you stand 100 meter from a wall, if you have a wall and you stand 100 meter away from the wall, and you should have a friend with you, and you clap your hands. When you clap your hands, obviously you immediately hear the sound of your clap. And when you clap your hand, your friend should start a stopwatch. And then you should wait. And obviously the sound waves will produce, they will spread in all directions. So the sound waves which will go towards the wall, from the wall, they will be reflected and they will come back. And when they will come back, and then you will hear the echo. So when you hear the echo, stop the stopwatch. See? So you have noted down the time the sound wave has taken from the source of the sound going to the wall, and from the wall coming back to the source. You see? And we already know that distance. So if, for example, I'm standing 100 meters from the wall, so the sound has traveled 100 meters from the source to the wall and reflected from there, and 100 meters back to the source from the wall. So if the distance between you and the wall is d, suppose it's d, then the sound covered a distance d and reflected, and also covered again the distance d. So the distance covered is 2d, if the d is representing the distance between you and the wall. So the echo, the sound waves which are giving you the echo, they have traveled how much distance? They have traveled 2d distance. And then divide that distance 2d with the time on the stopwatch, and that will give you an estimate of the speed of the sound. That can be a question in the ATP also, remember that. An estimate of the speed of the sound can be made directly if you stand about 100 meters from a high wall or building and clap your hands. Echoes are produced when the clapping rate is such that each clap coincides with the echo of the previous one. The sound has traveled to the wall and back in the time between two claps. One interval, that is one interval. By timing 30 intervals with a stopwatch, the time t for one interval can be found. Also knowing the distance d to the wall, a rough value is obtained from speed of sound can be found by this formula, 2d divided by t. The speed of sound in air can be found directly by measuring the time taken for a sound to travel past two microphones separated by a distance d. We will actually look at into this experiment. He's talking about The speed of sound in air is distance traveled by the sound by the time taken. Another very important thing, a small thing but frequently asked in the question in the paper, you see, every wave has a frequency, and same way the sound waves also have frequency. In 1 second, how many waves are passing from a point? That is called the frequency. Frequency is also the reciprocal, or we say reciprocal of the.
Time period.
Sorry, I cannot hear you.
Sir, time period. Time period.
Sorry.
Time period.
Yeah, time period. That the speed of the sorry, the frequency is the reciprocal of the of your time period. So, but the time period should be in seconds. That is a precaution regarding this. Okay. So now you see, we can. So the frequency which is measured in hertz. So the sound waves also have frequency. The frequency, the human ear is not able to hear all sound waves, the frequency, all the sound waves of all the frequencies. No,
Sir,
we can
I think
hear
so that is about.
only particular. We have a range of frequency, and that range is called audible frequency range. And if the sound is less than that range, we cannot hear it. If the sound is the frequency of the sound is more than the upper limit, then we cannot hear it. So the human ear, a normal human ear, can hear the sounds from 20 hertz to 20,000 hertz. Remember these numbers. They are from exam point of view, they are very important, because in MCQs they test this idea very frequently. The human ear, 20 to 20,000, 20 to 20K. Okay, K means kilo. So 20 hertz that to 20,000 hertz. This is the range. If the sound waves have a frequency in this range, the human ear will be able to hear it. If if the frequency of the sound is less than 20 hertz, the human ear do not respond to it. And if the sound is the frequency of the sound is more than 20,000 hertz, we are not able to hear it. So you see, the you know the human ear is able to hear the sounds whose frequency is between 20 hertz to 20,000 hertz. This is called the audible frequency range. Okay, this is a very important idea. Okay, the sound waves whose frequency is more than 20,000 hertz. Remember these words. Okay, the sound waves whose frequency is more than 20,000 hertz are called ultrasound. You must have heard this word. It's frequently used in our daily life. So the sound waves whose frequency is more than 20,000 hertz, they are called ultra sounds. And the sound waves whose frequency is less than 20 hertz, they are called infrasound. And from 20 to 20,000 hertz, that sound these sound waves are called, they are called audible frequency range. The sound in the audible frequency range, and we will be
Sir,
able to hear them. Okay,
excuse me, sir.
so I hope you understood this. Okay, so
Excuse me, sir.
here we are going to talk about
Sir, I need
an
a question.
experiment. This is another experiment, and
Excuse me, sir.
so in this experiment, what we do, this experiment, yes,
Sir, I was asking that if in case we hear a sound that is up to 20,000 hertz, will our hearing ability be damaged?
No, 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 not at all. Not at all. Your ear will not respond to it.
Okay, sir.
Okay? You will feel nothing. The damage
But sir,
to the
what
ear
about
is done by the intensity of the sound. If the intensity is too much,
sir? What
then
if a
it
person
might be
hears
damaging.
a sound wave
The
with a
intensity,
frequency?
but the word I just used, that is not in your syllabus actually. So that is
Sir,
included in the 10 metric physics, and in when you will go in A levels or in FSC, there you will study about that. Okay, so by the frequency, no, there will be no damage. Your ear will not respond to it. Okay,
sir,
so you see there are lot of explosions happening in the outer space, and there are a lot of sounds produced by different objects and different animals also, who the sounds are out of the this audible frequency range. Either they are infrasounds or they are ultrasounds, so we do not respond to them. So we are not able to, we do not feel, we feel nothing. Okay, okay, so for example on your screen, let me take it to the, let me do that. We will read it about it. Okay, so now you see here on your screen, I hope this is visible to you. uh, this is an experiment in which we can find out the speed of the sound. The setup is very simple. uh, this is a digital timer. So when the mics, here we have set two mics. This is the mic number one that he's calling it the start microphone, and here I have a second microphone, and he's calling it the stop microphone. We can also call them microphone number one and microphone number two. So here I have a hammer. So what I will do, I will strike some surface with the hammer, so the sound will be produced. So I have placed these microphones at a particular distance. For example, you can place them at a distance of 2 meters away from each other, or you can put them like a distance of 1 meter apart. And whatever distance you put these both the mics, whatever you take the distance between both the mics, the important thing is that we know that what is the distance between both these mics. Okay, so for example, I have placed myself the mic number one, the start microphone, and the mic number two, stop microphone, and I know what is the distance between them. I can measure the distance between them with a measuring tape, and they are just 1 meter or 2 meter apart. And once I know the distance between both the mics, here I have a digital timer. It will tell you whenever there is some sound in the microphone the start microphone, and whenever there is a sound in the stop microphone. When there is a sound in the start microphone, the digital timer will start counting the time. And when there will be a sound in the stop microphone or the microphone number two, the digital timer will stop. So, because it will be a very short time, you cannot measure it with the stopwatch because the time is less than the human reaction time. So, what will happen? The digital timer will tell you the exact time the sound waves took from microphone number one to go to microphone number two. The timer, this digital timer, it can measure very small lapse of times, and it can measure very short times. So it will tell you that how much time the sound waves took to go from the start microphone to the stop microphone. So what you will do, you will set everything. So you will bang this hammer on some solid thing. So a sound will be produced. This microphone number one will catch this sound, and this digital timer will start counting the time. Then the sound waves will travel, and when they will reach the stop microphone, the timer will stop. So the timer will tell you, the timer will tell you how much time the sound has taken to cover the distance d. Suppose the distance between both the microphones is d. So once you know the distance between the both the microphones, and you know the time taken for the sound to travel from the micro start microphone to the stop microphone, you simply divide the d distance with the time taken, the time shown by the digital timer. And this is how you will be able to find out the speed of the sound in a lab. Do you understand?
Yes, sir.
Hello? Okay. Uh, Sometimes this come in the paper and you have to write down this experiment also. Okay. So let us read this. I can read it for you. Okay. It says set two microphones about a meter apart and attach one to the start terminal and the other to the stop terminal of a digital timer as shown in the figure 13.5, the figure I just showed you. The timer should have millisecond accuracy, measure and record the distance d between the centers of the microphones with a meter ruler, with a small hammer and metal plate to one side of the start microphone, produce a sharp sound. When the sound reaches the start microphone, the timer should start. When it reaches the stop microphone, the timer should stop. The time displayed is then the time taken for the sound to travel the distance d. Record the time and then reset the timer. Repeat this experiment a few times and work out an average value for t. Calculate the speed of the sound in air for from the equation is d divided by t. Okay, so I hope that you have understood this idea, and let me show you another experiment. And let me show you another experiment. This diagram, which is right now being is showing on your screen, let me increase the size so you can see it. Okay, this idea is same. In this, we have this is the same experiment we just discussed. Little bit difference. Here I have a speaker that will produce sound. Here I have the microphone number 2 and the microphone number 1. And here we have oscilloscope. Oscilloscope it shows display, and in the display it can show you the sound waves. Okay, so what will happen when I will switch on this, I will produce a sound. When the sound will reach the microphone number 2, so the display will be flat, and when the sound wave will reach the microphone number 2, there will be an up and down in the display. So when the sound wave will reach the microphone number 1, here the it will be flat, but then it will be up and down. So on the x-axis, the display is like a graph. It has x-axis and it has y-axis. On the x-axis, the time is shown. So from the graph, you can tell, if I take the print of this display. So from the graph, the disturbance shown on the microphone number 2 and the disturbance shown on the microphone number 1. From there, because the x-axis is representing time, I can check that how much is the time between the disturbance shown on the microphone number 2 and microphone number 1. So that will give me the time, because the x-axis of the display of the oscilloscope is representing time. So from the oscilloscope, I can tell the time taken for the sound wave to move from the microphone number 2 to microphone number 1. And because we have placed both the microphones ourselves, so what we can do, we can measure the distance between them, and let's say the distance is d, and you can divide it with the time which is coming from the oscilloscope's display. And when you divide D with the teeth, you will be able to find out the speed of the sound. So you see, this is the second experiment which we have studied about how to find out the speed of the sound. One was with the claps and the echo, and then we have studied the using the microphone and a digital timer, or two microphones and an oscilloscope. So another very important experiment, which is sometimes you have to write about it, that how you can find out the speed of the sound. So for measuring the speed of the sound, we have to go into some area which is clear, means it's flat, it's clear, the visibility is good. So, for example, you see here they are in the ground, and the both here you can see I have shown here that there are two parties. One is on this top, and the other is on that top, and there is nothing between them, and they are like 1 kilometer apart. So if they are 1 kilometer apart, so you see the boy here, this the left sided the boy on the left side, he has a flash gun, and this boy on the other side has a stopwatch. So let me call this boy as A. Let the boy on the left side, let us call it the boy A, and let us call this as boy B. Okay. So what will happen that the boy A will fire the flash gun, and this boy B, when he see the flash, he will start the stopwatch, and after after a after a delay of some time, he will hear the bang of the flash gun. So when he hears the bang of the flash gun, he will stop the stopwatch. So you see, he has basically noted the time the sound wave has taken to cover this 1 kilometer, or whatever is the distance. The distance should be in kilometers. So once you know the distance between both the boys, boy A and boy B, and you have got the time the sound wave took from moving from boy A to boy B, you simply divide the distance with the time which is shown on the stopwatch. And that will give you an estimate of the speed of the sound. But in this, there's a problem because you are doing this experiment in open air. There can be a problem because, for example, if there is wind blowing, for example, if the wind is blowing from left to right, and the boy A has the flash gun, then that wind will increase the speed of the sound. But if the wind is blowing from right to left, and the flash gun is in the hand of the boy A, which is on the left side, so when you will do this experiment, the wind will be opposing the sound waves. So the sound wave speed, when you will calculate it, it will be less than what the value is normally. So to overcome, or to reduce this error, what we do, one in the one setting, what happens, the boy A uses the flash gun and the boy B will be using the stopwatch, and they will calculate what is the speed of the sound, and then they will switch the roles with each other. Now the boy B, which is on the right side, he will have the flash gun and he will fire the flash, and the boy, which is boy A, he will have the stopwatch and he will time. Now the sound will be traveling towards the left. So they will do the same process. When he will fire and the boy A will see the flash, he will start the stopwatch, and when he will hear the bang, he will stop the stopwatch. So they will divide the distance between both the boys with the time which is shown on the stopwatch, and that will give you the time, and divide the distance with the time, and that will give you an estimate of the speed of the sound. Now you have both the speeds. You have the speed when the sound was traveling to the from left to right, And you also have the speed when the sound was traveling from right to left. Distance divided by time. Distance divided by time is the simple formula. Speed is equal to distance divided by time. So you have the speed of the sound. You have estimated the speed of the sound in both the directions. When the sound is traveling from the left to the right, and from the right to the left. So then take the average of both the speeds, and this will give you a pretty accurate estimate of the means accurate estimate of the speed of the sound.
So are we gonna take out the average of those?
Unfortunately, in my cell phone, the sound is very low. So what are you saying?
Sir, I was asking that do
Hello?
we need to take out the average of the both?
Yes, yes, we will take the average of both the speeds which we just calculated, and that
Okay,
will
sir.
be the speed of the sound. So this is how we find the speed of the sound. So I let me. Uh, so Soji, thank you very much for this session. I'm stopping it here. So thank you very much and have a good day. I hope that you have understood.